Dear students, now we are going to another important concept which deals about primitive roots and quadratic residues. We know what is a primitive root. Also we know about quadratic residues. Now combinedly it gives a theorem. The theorem states that let G be a primitive root mod P where P is an odd prime means P is an odd prime means P differs from 2. Then the even powers, that is G square, G to the power 4 etc. G to the power P minus 1 are quadratic residue mod P, and the odd powers means G, G cube etc. G to the power P minus 2 are quadratic non-residue mod P. So these are the relation between the primitive root mod and the quadratic residues and quadratic non-residues. If G be a primitive root mod P, then the even powers, where P be an odd prime, then the even powers G square etc. G to the power P minus 1 are quadratic residues. How to prove this one? So the proof is in this way. Let n is even. Suppose n equals some 2m. Then what about g power n? G to the power n equals g to the power 2m. That equals g to the power m whole square. G to the power m whole square. But what is g? We know that g be a primitive root mod p. G be a primitive root mod p means this exponential of g mod p equals some phi of p. Okay, g be the primitive root mod p means exponential of g mod p is phi of p. That means g to the power phi of p is congruent to 1 mod p. G to the power phi of p congruent to 1 mod p means what is phi of p? Since p is an odd prime, phi of p is p minus 1. So g to the power p minus 1 congruent to 1 mod. So here g power n equals g to the power m the whole square. So that means this g to the power n congruent to this g to the power m whole square mod p. Why? Because g is the primitive root mod p according to that arguments. Agreed. G to the power p minus 1 is congruent to 1 mod p. So let x equals g to the power n. X equals g to the power m means this g to the power n congruent to x square mod p. Agreed. But congruence is symmetric. This implies x square congruent to g to the power of n mod p. X square congruent to g power n mod p means this g to the power n is a quadratic residue mod p. Now we know that there are p minus 1 by 2 quadratic residues and p minus 1 by 2 quadratic non-residues. So the even powers g square, g to the power 4 etc. g to the power p minus 1 are strictly p minus 1 by 2 numbers. Agreed. There are p minus 1 by 2. P minus 1 by 2 distinct even powers of g, which are g square, g to the power 4 etc. g to the power p minus 1, and we also know that there are p minus 1 by 2 quadratic residues. So these are the quadratic residues. So the remaining p minus 1 by 2 are quadratic non-residues. Actually what are the remaining? The remains are odd powers, that is g cube, g cube etc. g to the power p minus 2. These also are distinct p minus 1 by 2 odd powers. So according to our arguments, there are p minus 1 by 2 quadratic residues and p minus 1 by 2 quadratic non-residues. Hence there are p minus 1 by 2 or the even powers g square, g power 4 etc. g to the power p minus 1. These p minus 1 by 2 distinct even powers of g are quadratic residues. Then the remaining are odd powers of g are quadratic non-residues. Agree. That is what we required here. Here, when n equals 2m, it is n is even, then g power n equals g power 2m means g power m whole square. That is g power n congruence to g power m whole square mod p. Why? Because g is primitive mod p. G is okay. G is primitive mod p means g to the power p minus 1 is congruence to 1 mod p. Enough. Okay. Now, we are going to another important result, that is existence of primitive root mod p power alpha. This is existence of primitive root mod p to the power alpha. So far, first we consider, let g be a primitive root mod p. First so this is for reaching the necessary condition for the existence of primitive root mod p power alpha. Let g be the primitive root mod p power alpha. P. G be the primitive root mod p means g to the power phi of p is congruence to 1 mod p. That is, since p be an order prime, and so this is g to the power p minus 1 congruence to 1 mod p. Why? Because g is the primitive root mod p. G is primitive root mod p means exponential of g mod p equals phi of p. That means g to the power phi of p is congruence to 1 mod p. Since p is an order prime, phi of p is p minus 1. So it is finally g to the power p minus 1 is congruence to 1 mod. Now, what is phi of p square? We know that phi of p square equals p square minus p. This is a non-result. P square minus p means it is p into p minus 1. Okay. But what is p? P is an order prime, means p greater than 0. P greater than 0, and so clearly this p square, phi of p square, it is strictly greater than p minus 1. Means p into p minus 1 greater than. So before going to this one, since p greater than 0, we know that p into p minus 1 greater than p minus 1. But what is p into p minus 1? That is phi of p square. Means phi of p square greater than p minus 1. Okay. So, if g to the power phi of p square congruence to 1 mod p square, what happens here? If g to the power p minus 1, if g to the power p minus 1 congruence to, we know that g to the power p minus 1 congruence to 1 mod p. Why? Because of the choice of g. G is the primitive root mod p. But if possible, g to the power p minus 1 is congruence to 1 mod p square. What happens here? If g to the power p minus 1 is congruence to 1 mod p square, then surely g is not primitive root mod p square. Why? Because phi of p square greater than p minus 1. If g to the power p minus 1 is congruence to 1 mod p square, then this g is not primitive root mod p square. G is the primitive root mod p square means this p minus 1 be the least positive integer which satisfies this relation. Okay. But here phi of p square greater than this p minus 1, then this if g power p minus 1 is congruence 1 mod p square, phi of p square need not be equals p minus 1. When this g is a primitive root mod p square, this p minus 1 should be equals phi of p square. Okay. When this p is a primitive root of g is a primitive root mod p, phi of p equals p minus 1. This exponent should be equals this modulo. Agreed. But here if g to the power p minus 1 is congruence to 1 mod p square, that means g is not a primitive root mod p square. This becomes the primitive root mod p square only when this modulo p square should be equals this exponent. But we know that the exponent should be less than this phi of p square. So this is not the least positive integer. So it is g power p minus, if g power p minus 1 is congruence 1 mod p square, we know that then g is not a primitive root mod p square. Agreed? Okay. That means if g is, then we reach a condition, that is if g is a primitive root mod p square, then g to the power p minus 1 is strictly incongruent 1 mod p square. So this is a necessary condition for the existence of primitive root mod p power alpha. Mean for alpha greater than or equals 1. That is, g is a primitive root mod p. This is the condition. If g is a primitive root mod p, then g is not a primitive root mod p square. If g is a primitive root mod p, then g is not a primitive root mod p square only if g to the power p minus 1 is strictly incongruent 1 mod p square. Okay, g to the power p minus 1, if it is congruent 1 mod p square, g is not a primitive root mod p square. Why? Because this becomes primitive root only when the module equals this exponent. But we know that phi of p square is this module is same as phi of that module. So exponent is same as phi of that module, but the phi of p square is strictly greater than this exponent. So this g power p minus 1 is incongruent 1 mod p square here. Okay, that is, if g is primitive root mod p, then g is not a primitive root mod p square only when g to the power p minus 1 is incongruent 1 mod p square. Agreed? So this is the necessary argument. Okay.